Let's
Good
go.
night. Today we will present our big data projects. My name is Valentina Corrales.
My name is Salma Jawhari.
My name is Aminata Diakité.
My name is Ibrahim Touré.
Okay, so first I would like to introduce a presentation of the code. Do like a little bit of a brief presentation. So this notebook outlines the development of a basic chess playing agent for the Fight and Google Efficient Chess AI challenge on Kaggle. The objective is to create a functional bot capable of making legal chess moves within a controlled simulation environment. I will speak a little bit about some aspects. First is the environment setup. The code utilizes the Kaggle environments module to simulate the game and test the agent. The chestnut library is used to parse board states in FEN format and generate legal moves. The initial approach described in the Fight and Google Efficient Chess AI challenge, where the agent selects to move randomly from legal option, is not a machine learning. This approach is rule-based, meaning the agent makes decisions without learning from past experience or improvement over time. It simply follows predefined logic to select valid moves, but it doesn't adapt or optimize either strategy. This approach does not utilize machine learning or deep learning techniques. The second one is the agent logic. The agent in this implementation is basic and non-learning. It randomly selects a move from the list of legal actions. Here we have a little example that imports random moves. And this ensures that the agent only plays valid moves but lacks any strategic logic or foresight. The third one is visualization. Simple word visualizations are included to help track the game's progression and visualize the agent's selected moves. These visuals aid in identifying patterns or mistakes, such as missed captures or unnecessary sacrifices. The fourth one is testing. The notebook includes code to run simulated games between agents, such as random versus random. The agent's performance is measured in terms of its ability to function correctly in the game environment rather than in terms of wins. Last one but not least is the next steps. The random move selection as a baseline for further development. Future improvements will involve integrating Hurt's logic, position evaluation, and possibly reinforcement learning to make the agent smarter or more strategic. So we'll do like a little example. Let's walk through a simple scenario. In a simulated game between two random agents, each agent randomly selects move from the available legal actions. If agent 1 makes a move, the board state is updated, and then agent 2 randomly picks a move. The game continues until a termination condition is met, for example, checkmate or stalemate. Despite the lack of a strategy, the agent successfully follows the rules and makes legal moves, providing a foundation for further enhancements.
So we choose as a problematic, how does a model use a game environment data to choose a move randomly? Let's diving into the presentation of the subjects and tools for the Fight and Google Efficient Chess AI Challenge. First, the Fight and Google Efficient Chess AI Challenge is an AI competition hosted on Kaggle, aimed at building chess playing agents that can make strategic moves in a simulated chess environment. The challenge provides an opportunity to create artificial intelligence models capable of understanding the game of chess, analyzing boards positions, and selecting optimal moves based on the current state of the game. Participants are encouraged to explore various AI techniques, including rules-based systems, heuristic evaluations, and reinforcement learning to build an agent that can play a high level. The primary goal is to develop a bot that can play the game of chess, make valid moves, and potentially wins against other agents in a simulated environment. The competition emphasizes efficiency in both the implementation and the decision-making process of the agent. So the tool that we used, our first a random agent, is a type of intelligent agent that selects its action purely at random without considering the state of the environment or specific objectives. In the context of chess, such as an agent would randomly choose a valid move from the available options without evaluating the current position or anticipating the consequences of its choice. How a random agent works. First, the perception of the environment. So the agent identifies the possible actions in the current situation. Then, from these valid actions, the agent randomly selects one. We call this step random selection. Finally, the agent performs the selected action without any prior evaluation or strategy. This type of agent is often used as a baseline to evaluate the performance of more sophisticated agents. By comparing the results of an intelligent agent with those of a random agent, the effectiveness of the strategies implemented can be measured. Also, easy to implement, a random agent is limited in its ability to perform complex tasks or achieve specific objective as it does not take the environment's information into account when directing its actions. So here's the tools. First, Kaggle Environments. The Kaggle Environments module is a key tool used to stimulate the chess games for the challenges. It provides an interface to run and test agents in an isolated, controlled environment. This tool allows for multiple agents to play against each other, simulating a variety of scenarios to assess the agent's performance. It also supports customization of the game environment to fit the challenge requirement. The key features are simulation of multiple game environments, support of agent-to-agent interaction, and building functionally to run and test the performance of agents. The second tool is Chestnut Library. The Chestnut Library is used for managing chessboard states. It parses board position in Fan, forces Edwards notation format, allowing for easy representation and tracking of the game. The library also helps generate legal moves for a given position, which is essential for the agent to make valid choices. Its key features are parsing board states in Fan format, generating legal moves, updating the board state after a move. Then we have Python. Python is the primary programming language used to implement the chess agent. The code involves defining the agent's logic, which is responsible for selecting legal moves based on the current game state. Python's simplicity and flexibility make it ideal for rapid prototyping and experimentation in AI development. Its key features are high-level programming language, extensive libraries for AI and simulation, for example, random for basic move selection, and flexibility for implementing different AI techniques and models. And finally, we have the Matplotlib visualizations. Simple visualizations using tools like Matplotlib can be implemented to track and display the progressions of the game. These visual tools provide a clear view of the board and the moves made by the agent, allowing for better understanding and debugging of the agent's behavior. The key features are visual representation of the chessboard, displaying the game's progress, and tracking the moves and performance of the agent. The subject of the FIDE and Google Efficient Chess AI Challenge offers a platform for AI development in the domain of game theory, specifically focusing on chess. The tools used in the challenge Kaggle environment, Chestnut, Python, and visualization libraries provide a robust and flexible framework for building and testing chess playing agents. These tools enable participants to experiment with different AI techniques, improve the efficiency of their agents, and contribution to AI advancement in strategic game like chess. Now, let's talk about the model used and definition and its definitions. The model used is in this notebook is an agent based on random move selection within Kaggle chess simulation environment. It does not rely on machine learning or advanced artificial intelligence models. Here are the key characteristics of the model used. About Kaggle environments, the code utilizes is Kaggle environments library to create a chess game environment. The agent operates within the framework defined by the Kaggle competition. Then about the random move selection agent, we have the agent randomly selects a move from the available legal moves. And second, it does not consider board position, strategy, or game evaluation. And finally, about the no learning or optimization. This is not a machine learning model too, no neural networks or supervised algorithm, and the agent does not memorize games or improve over time.
Okay, now we are going to see a detailed interpretation of the code in the Kaggle notebook for creating a chess playing agent. First, the code starts by activating Kaggle environment and setting up a chess game environment. So as we can see, make chess debug equal true is the part that creates an environment to simulate chess game. This environment is used to test the performance of AI agents. The model used in the notebook is an agent that for defining a simple agent. The model used in this notebook is an agent that randomly selects a move from the possible legal moves. So as we can see, obs represent the current game, like the pieces, the legal moves, etc. Config provides information about the game, like duration and specific rules. Obs attraction mask non-zero retrieves the list of legal moves. And random choice is they randomly select a move without any strategy. The model plays a valid move, but without any strategic thinking. But there is some limitation. Indeed, it follows no strategic logic and play like a random beginner. Then for simulating a game with this agent, the code runs a game by pitting the random agent against itself. So random agent runs a game with three agents playing randomly, and end render display the game in a graphical format. So as a result, it's a complete chess game that is played, but with no intelligence or strategy. And then we have the last part that is submitting the model to Kaggle. So once the model is defined, it can be submitted to the Kaggle competition. So for this code, it's saved. This code is saved the model as a file named submission.py to be submitted to Kaggle. And the write agent function writes the agent code into a file that make it compatible with the competition evaluation system. So what the code does, it creates a simple engine to play chess. It chooses the Kaggle environment to test the agent. It play random games and submit the model to Kaggle. But there is also issues to the model, like the lack of strategy. The agent does not calculate the best move. There is no memory. It doesn't adapt to the previous game. And they cannot win against a strong AI. It plays randomly and doesn't have any strategic intelligence. So for the possible improvement, we can replace the random algorithm for better decision making and position evaluation to make smarter moves. And we can also integrate a machine learning model to learn from past game. So is it a large model or a small one? The model is used in the notebook is a small model. In fact, it is not even a machine learning model, but simply a random function that selects a move from the valid ones, as we saw before. So why is it a small model then? So there is no artificial intelligence. It does not rely on a neural network or a unsupervised learning algorithm. There is no advanced there is no advanced computation. Unlike chess engine like Stockfish or AlphaZero, it does not evaluate position. And there is a low complexity. It performs a single operation, like choosing a random move from the available options. So what is the problem that we are addressing? And what are we developing the model for then? We are developing the model to serve a baseline chess playing agent for the feed and Google efficient chess AI challenge on Kaggle. The purpose of this model is to interact with a simulated chess environment, ensuring that it can legally participate in the game by selecting valid moves. While the initial implementation is rule-based and purely random, it laid the foundation for more advanced AI strategy that could be integrated later. This model is primarily being developed for experimentation, evaluation, and future enhancements in chess AI. It acts as a starting point for exploring different techniques from heuristic-based decision-making to reinforcement learning and neural networks. The problem we are addressing, the problem we are addressing revolves around the creation of an automated chess playing agent that can interact with a simulated game environment specific within the constraint of the feed and Google efficient chess AI challenge on Kaggle. The primary objective is to develop a functional baseline model that can legally participate in chess game by making valid moves. And this serves as an entry-level implementation, providing a foundation for future enhancements, future advancements, in AI-driven chess strategies. So to achieve this, the model must be capable of interpreting the chessboard state, identifying all legally permissible moves, and executing one of them during its turn. But however, the initial implementation follows a rule-based approach, meaning that the agent does not analyze board position, does not evaluate threat, or it does not anticipate future game scenarios. Instead, it simply randomly selects a move from the list of legal options without applying any strategy logic, as we could have seen before that. Since this initial agent lacks learning capability, it does not adapt to different opponents, nor does it improve its decision-making over time. It remains deterministic in its randomness, ensuring that all its moves comply with the chess rules, but without any tactical or positional understanding. This makes it an effective baseline model, a benchmark against which more sophisticated AI techniques can be measured.
Okay, so for the input and the output, so one the problem we're solving, so the goal is to build a functional chess playing bot that can participate in the FIDE and Goal Chess AI challenge on Kaggle. So the bot must play a legal chess move based on the current state of the board using a standardized format. So this is not a learning model, it's a heuristic rule-based agent that simulate basic decision making with a simple hierarchy of priorities. So first try to check math, try to capture, try to promote, and otherwise play a random legal move. So for the input, at each turn, the bot will receive an observation, so the object OBS from the environment. So this object include a if en string, so for seeds Edward notation that describe the board state. The agent use that string to reconstruct the current board and using the chestnut library. So with that, he will generate a list of legal move in UCI format. So E2, E4, or G1, GF. So that's bring me to the output. So the agent will return a single move in UCI format, a string like E2, E4, or that describe the move to make. So this move will be legal because it generates from the get move of the chestnut board. It's chosen based on the agent internal priorities, so checkmate, capture, promote, or else random. So for the example, you see that return if F7, F2, this tells the environment to move the piece from square F7 to F2 based on the standard UCI notation. So Unlike a random agent that blindly pick a legal move to chessboard, that agent will simulate each move and check if it ends the game. Look for ways to gain material, detect opportunity to promote a pawn, and still guarantee a legal move, if not better option of round. So it's a basic but a strategic agent and a great foundation for future improvements like adding evolution courses or using minimax or integrating machine learning. So there is an example of how the agent play. So in black we have our agent, and in white you have a random agent.
So now, to conclude, this study explored the development of a simple chess playing agent as part of the FIDE and Google Efficient Chess AI Challenge on Kaggle. The objective was to create a functional bot capable of selecting legal moves within a simulated environment, serving as a baseline for more advanced AI-driven strategies. The agent designed in this project follows a purely deterministic logic, selecting its moves randomly from the available legal options. The initial approach described in the FIDE and Google Efficient Chess AI Challenge does not involve machine learning. It is a rule-based approach where the agent makes decisions without learning from past experiences or improving over time. It simply follows predefined logic to select valid moves with no adaptation or strategic optimization. However, incorporating machine learning into this challenge is entirely possible. For instance, participants can implement reinforcement learning, a technique where the agent improves its decision-making process through trial and error. In this case, the agent will receive feedback, such as rewards for winning or penalties for losing, and gradually adjust its strategy to maximize performances. Here's how machine learning could be applied. So the first proposition is reinforcement learning. The agent learns by playing multiple games and receiving rewards based on its performance. For example, winning a game or avoiding checkmate. Over time, it refines its move selection based on this feedback, learning to improve decision making. The second proposition is neural networks. These models could be used to evaluate board positions, recognize recurring patterns, and select the most promising moves based on past game data.
During testing, the agent demonstrated its ability to follow the rules of chess by playing only legal moves. However, its limitations are evident. It lacks strategic foresight, does not retain memory of past games, and has no learning mechanism, making it competitive against more advanced chess engines. Despite these constraints, this random move agent serves as a crucial reference point for evaluating future improvements. Potential optimizations include integrating heuristic techniques such as the minimax algorithm with alpha-beta pruning, which will allow the agent to analyze potential consequences of moves and select those with the best outcomes. Deep learning approaches using TensorFlow or PyTorch could also be explored to enhance the agent's positional analysis capabilities. Additionally, incorporating Stockfish as a reference engine could aid in training a more robust and competitive agent. Although this initial model is simple and lacks artificial intelligence, it provides a solid foundation for developing a more sophisticated agent. By integrating machine learning techniques, this agent could evolve into a more strategic and competitive player, demonstrating the potential of an AI in game theory and automate decision making. The main difficulty was the lack of strategic foresight, as the agent randomly select legal move without evaluating their consequences. Unlike machine learning-based models, it did not learn from past games or adapt its strategy, making it non-competitive against advanced chess engines. Additionally, implementing more sophisticated algorithms, such as minimax with alpha-beta pruning or reinforcement learning, will require significant computational resources and a well-designed reward system to guide the learning process effectively. Despite these limitations, the project provides valuable insights into AI decision-making in chess. It serves as a baseline for future improvements, demonstrating the difference between rule-based and learning-based approaches. Moving forward, integrating reinforcement learning, neural networks for position evaluation, or heuristic-based algorithms can significantly enhance the agent performance. This project reinforced the importance of scalability and adaptability in AI, showing how combining search techniques with machine learning can create more intelligent and competitive gameplay in agents. Thank you for your time, and I hope like it was a good presentation for you.
Thank you.
Thank you.